So let's get into valence bond theory now with this idea of pi bonds and how these result from non-hybridized orbitals. Remember, this is a second or third connection between elements. Right? The first connection, remember, is the sigma bond. And that's from the idea of hybridized orbital. So we have those two distinctions, right, as far as the non-hybridized orbitals and the pi bonds, and then hybridized orbitals and this idea of a sigma bond. So let's look at, an example of, look at a couple of them, but let's start off with formaldehyde here. Formaldehyde has, a structure that looks like this. This is what, trigonal planar, and we have, three groups. So if we look at our, our carbon atom with this 2s and 2p valence shell, right now we're going to hybridize three orbitals, right, because of that idea of three groups. So, we're looking at taking these three and creating now three new orbitals, which we have here. And then we still have one that's left over, right? We start with 4, we end with 4. And so each one of these is an sp2 hybridized orbital. And then up at the top we have a 2p. And then if we put our electrons in, we have electrons now, singularly populated. So the top here with our 2p, that's where our pi bond is going to come from, right? That's the non-hybridized orbital. And then here is where our sigma bonds are coming from. These are the hybrid orbitals. So here is where our sigma bonds come from. Again, that's our first connection. So if I look at my carbon atom, it's going to have then, those three groups set up in such a way for that trigonal planar structure. If we count up electrons, oxygen still has one that's unpaired, and carbon as well has one that's unpaired. So we have our three sigma bonds that are here, and it's these two that are left over is where, the pi bond will basically form. So if we now draw the structure maybe more flat. So I'm going to have my carbon atom here. I have the oxygen bound to it. And now that means that this one hydrogen is actually coming out at me. And my other hydrogen is going back. So that's the structure that we have off to the left, but just kind of rotating it on its side. And what we have with each one of these elements that's left over, right? Our carbon atom has 1 electron in it, and notice that that is actually in a 2p orbital. If we look, scrolling up a little bit up to the top right, we've already handled the 3 electrons at the bottom with the sp2 hybridized set for the first connection for the sigma bonds, but yet we saw this 1 extra electron that's actually out there in the 2p. And we actually find the same thing is going on with the oxygen. Let's just concentrate on the carbon for right now. So the oxygen also has this 1 orbital that's kind of left over with an electron within it. Where does the, as far as the hybridization, we'll find that the oxygen is actually also sp2 hybridized, right? It has 3 groups. And so the lone pairs that are there, right, are part of those hybridized actual orbitals. If we were to actually draw them in, we would see, much like with the hydrogens, we would see a lobe going back and a lobe coming out at us. So just as, even the oxygen is hybridized as well. And if we were to look at its grouping, we would see something very similar to what we see with the carbon. So that lone pair, right, we have the 2 sets of lone pairs. Those are part of those sp2 hybridized orbitals as well, going forward and going backwards. So what's left over is we have, in both cases with our carbon at the top right with the 2p and our oxygen at the bottom with the 2p, that now we have these 2 electrons that are actually kind of right next to one another, but they're not in between. They're above or below. And that's the development of the pi bond. So if we take that molecule we have above, just keeping everything here the same, so just want to show our lone pairs for the oxygen and where they're at. I'm going to come, I guess, a little over here, give a little more space, sorry. We have our hydrogen going back, our hydrogen coming forward. And so what we find here is this lobe, they get close together. They get so close that they actually start to overlap. And so you have overlap above and below the plane. So the p orbitals overlap above and below the sigma bond. This makes sense if we think about it. There's already 2 electrons in between the carbon and the oxygen. So putting more electrons in between results in, greater repulsion forces. Again, we're talking about these similarly charged electrons, right? So that results in greater repulsion if we do it that way. However, if I can overlap and house bonding electrons in another region, say above and below the sigma bond, then repulsions are minimized. So I got 2 electrons that are in this pi bond, right? And the pi bond is the overlap above and below the actual plane of the carbon-oxygen or the carbon-oxygen sigma bond. So that's why we have this notion of pi bonds, is because, well, the sigma bond housing 2 electrons is already in between the 2 elements, and we can't put more electrons in between the 2 elements because of the fact that electrons are, negatively charged and they naturally repel one another. And so that just results in forces that just don't match. So now this idea of, using the p orbital and having, this idea, well, the p shape is this lobe above and lobe below an element. Well, now we can actually overlap those lobes, and that's what we're seeing here with this particular pi bond scenario. So that's what the pi bonds actually look like. And not only can we go above and below like we see here, we can also extend it further to in front and in back. And these structures definitely get a little bit tricky to draw, and I'm not grading anyone on art or anything like that, but it's just this visualization of how the bonding actually occurs with the actual valence electrons, hybridization, and then also these valence orbitals that are not hybridized. Now I have the 2 electrons here in the top part of the pi bond, but realize this is a probability idea. Like, all I know is that those 2 electrons that make up the pi bond could be found above or they could be found below, basically in that red area. Right? It's just the probability. I know I won't find them in between the carbon and oxygen. All right? So again, that goes back to that Heisenberg uncertainty principle idea again. So overall, I have, my normal structure like here, showing a little bit more detail with all the orbitals that are hybridized and indicating, the bonding scenario here in this picture as well. So we have, oxygens, or rather, maybe I should say it better this way, oxygen is also sp2. hybridized. Right, so both lone pairs are sp2, like we see there, going, we still see the trigonal planar geometry with the oxygen as well as with the hydrogen, right? They both have, I'm sorry, the carbon as well as the oxygen, we both have, 3 groups around them. So in one case, the one system is the sigma bond, the first connection, and then the second connection is the pi bond. So let's keep this in the mix with another example, just showing a little bit more of an involved nature. Stick to carbon and oxygen though, with CO2. So here we have our carbon atom in the middle with 2 oxygens on either side. We know that this would be a linear geometry. We have basically 2 groups. Around the carbon atom. Oxygen is going to be a little bit different here, right? Oxygen has 3 groups around it, right, with the carbon and then the 2 sets of lone pairs. So we're going to see, subtly difference in geometry, but we'll try to keep reinforcing, both ideas with the carbon and the oxygen. So showing, kind of the same schematic. Here we should be getting used to with carbon, right? We now need to hybridize 2 orbitals. Right, because of the notion of the 2 groups. And we end up now with 2 that are sp hybridized, and then 2 that are still as the 2p. So here will be now our new set of orbitals that we have. Oops. And we would have 1 electron in each one. So here is where our pi bonds are going to be coming from. Again, these are the non-hybrids. And then we have our sigma bonds down below. And those are from the hybrid orbitals that we have there with the sp hybridized. Right, so this is again that first connection with the hybridization. So if we were to draw that out, right, we'd have our carbon bound to each one of the oxygen atoms. Like this, we would have our 2 sigma bonds that we've laid out with the sp hybridized orbitals, and carbon still has 2. So oxygen, each oxygen has 1 unpaired valence electron yet to take care of with the double bonds, and carbon has the 2 to facilitate that. So if we now, kind of look at the molecule in terms of those orbitals, we end up with our carbon atom, right, having 2 lobes essentially now. here would be, one of those, and then we can draw another in terms of going back and going forward. Right, remember these are what's going to be now making the pi bond, are these last electrons that we have not hybridized yet. And if we scroll up a little bit, we see we have 2 electrons in the 2p orbitals, so we have 2 2p orbitals, electron in each one of them, and so that's what I'm drawing here with the carbon and its 2 sets of p orbitals, each one with 1 electron within. Oxygen here is sp2 hybridized. If we look at each oxygen atom, we have 1, 2, 3 groups. So if we were looking at our electronic configuration now for each one of those oxygens, we would have, they have the 6 valence electrons, so we have 1 in each before we start to pair. And so that means we have 2 lone pairs in our sp2 hybridized set. And then we have 1 sp2 bonding set for the single bond. And then we have 1 2p for our pi bond. So each oxygen can accommodate this. So we would draw, the lone pairs on that oxygen kind of flat, trying to show the 3-dimensional trigonal planar geometry here. Like I said, it gets complicated with these valence bond theory lobes that we have. So that oxygen is going to look like that, which means it has a lobe that's actually pointing up as well. There is our 2p orbitals, each one with an electron, and so we're going to see overlap there. And then the other oxygen is actually kind of on angle. So each one of the lone pairs is actually in the plane of the page. And so as a result of that, sorry, just making some room. As a result of that, now we have this unhybridized p orbital as well that's now kind of coming out at us and then going back as well. I'm going to try that a little bit differently here. I'm going to get it to kind of match what I want it to match. So kind of like that. And then we have our back lobe, which we could say is kind of behind that lobe, if you will. And then we have the back side of the purple. So we have this, pi bond overlap now that we could say that's in front and in back. And we also now have a pi bond set up for above and below. And so if we were to look at that, and this is going to be tricky, so don't worry about drawing this. Even I'm apprehensive about drawing this. So we have our 2 oxygens. one that's kind of flat, so one of the lone pairs is coming out at us, the other one going away. One going away. So we have that, and then we have the other oxygen. I'll leave that out for now. We have the above and below one, which is the easier one to really draw. And so there's the 1 pi bond that we have with its 2 electrons being shared. And then we have the harder one, which is, kind of coming out and going back. And then it also has its lone pairs as well. And so that is the other pi bond. And again, it's a probability thing as far as where to find those bonding electrons. For the red pi bond, we could find those 2 electrons above and below. For the purple one, we could find, those 2 either in front or in back. So if we draw our carbon monoxide, notice how I'm drawing the lone pairs, kind of drawing them already here with that 120 or trigonal planar geometry. But we have, our sigma bonds with that first connection. Those are the sp2, or I'm sorry, sp hybridized, for the carbon atoms. And then we have our first pi bond, and now we have our second pi bond in terms of carbon dioxide. So I know it gets a little bit confusing with the drawing, but I'd like us just to be able to recognize these lobes and this idea of electron density and where we can find these things. The last scenario, last example here for valence bond theory would be C2H2. And so here is our triple bond scenario. It's really much like the CO2 one, but instead of involving 3 atoms here in terms of pi bonds, we're only really involving 2. So we have kind of the same thing going on for the carbon, though. We have a linear geometry. Each carbon atom has 2 groups around them. So we actually have a similar setup in terms of the hybridization for our carbon in C2, in acetylene C2H2, as well as carbon dioxide. So we need to hybridize 2 orbitals because of our 2 groups. And so that gives us now our 4 orbitals. We have our 2p set that we haven't touched. We have our sp hybridized orbitals. Right there is where our sigma bonds come from, the hybridized nature. pi bonds coming from the non-hybridized nature of those orbitals. And we have one electron in each. So there is our first connection with the sp2 hybridized, I'm sorry, I apologize, sp hybridized orbitals. So here we now have our acetylene, showing the sigma bonds that we get. Each carbon has 2 sigma bonds, and that's coming from those sp hybridized orbitals. And if we then look, right, each carbon has, one electron that's left over. I'm sorry, 2 unpaired valence electrons that are actually left over. So that's where our pi bonds are going to be now being formed. And we see something very similar to the geometry we're seeing above, where we have, these are both in p orbitals, so we have, a red set of p orbitals which are aligned with one another. And then we have, a purple set of p orbitals that are also aligned with one another, so they're in the same axes. And so that's where we're now going to be seeing our pi overlap, is with the 2 p's that are red and the 2 p's that are purple. So we have the red set, that overlap above and below. And then we have the very much harder one to draw here, which is coming out and going back. Obviously a picture would be better, but I like to work on my drawing skills. A little practice, practice makes perfect. So if I were to draw this maybe a little bit better here with perspective, we have our one that's going down kind of in the back, right, underneath that lobe in the front. Where we find that other density with the red, and then going back, and we just have that lobe going back as well. So we can imagine maybe something that looks like this. It's really kind of like a tight ball there, if you will, to give us to our logic behind how are all these electrons hanging out. 6 sets of electrons between these 2 carbon atoms. Well, they're not in between them, right? We have 2 that are in between, we have 2 that are above and below, and we have 2 that are in front and in back. So we have our sigma bond right? And we have, two sets now of those pi bonds. So I know it's tough with the drawing and the 2D flat page here. So let's, take a look at a video here. It's a 3D, animated short on, just looking at these shapes. And I'm sure this visual will be much better than the cartoons I'm drawing. But I think with drawing them yourselves, you start to understand spatial relationships and where these orbitals actually are, where these electrons are being housed, and how these geometries, are all being put in together, right? So it's, again, this last bit with the model of valence bond theory. Check out this short video.
Let's examine the bonding in three molecules: ethane, ethylene, and acetylene. Click on one of the molecules to view an animation of the bonding in that molecule. First, consider the Lewis structure of ethane. Counting the number of VSEPR pairs of electrons around carbon 1, we find 4 VSEPR pairs. You should also count 4 VSEPR pairs around carbon 2. The VSEPR model predicts that the geometry about each carbon atom is tetrahedral. In valence bond theory, 4 sp3 hybrid orbitals have a tetrahedral arrangement. We can begin to explain the bonding in ethane if we assume each carbon atom is sp3 hybridized. Each hybrid orbital will contain one valence electron, accounting for the 4 valence electrons of each carbon atom. The bond formed between the two carbon atoms is called a sigma bond. A sigma bond is a covalent bond formed by orbitals overlapping end to end. The electron density is concentrated between the nuclei of the bonding atoms. In this sigma bond, 2 electrons are shared between the carbon nuclei. When we add the hydrogens, the remaining 3 sp3 hybrid orbitals on each carbon form sigma bonds by overlapping with hydrogen 1s orbitals. 2 electrons are shared in each sigma bond. A single bond is composed of 1 sigma bond. Lastly, rotation can occur about a single bond because rotation will not break the carbon-carbon bond. First, consider the Lewis structure of ethylene. Counting the number of VSEPR pairs of electrons around carbon 1, we find 3 VSEPR pairs. Recall that double and triple bonds are counted as single bonds in the VSEPR model. You should also count 3 VSEPR pairs around carbon 2. The VSEPR model predicts that the geometry about each carbon atom is trigonal planar. In valence bond theory, 3 sp2 hybrid orbitals have a trigonal planar arrangement. We can begin to explain the bonding in ethylene if we assume each carbon atom is sp2 hybridized. Each hybrid orbital will contain 1 valence electron, meaning that for each carbon we have accounted for 3 of its 4 valence electrons. The bond formed between the 2 carbon atoms is called a sigma bond. A sigma bond is a covalent bond formed by orbitals overlapping end to end. The electron density is concentrated between the nuclei of the bonding atoms. In this sigma bond, 2 electrons are shared between the carbon nuclei. When we add the hydrogens, the remaining 2 sp2 hybrid orbitals on each carbon form sigma bonds by overlapping the hydrogen 1s orbitals. 2 electrons are shared in each sigma bond. There is still one more bond to explain. Which orbitals overlap to form the second bond of the carbon-carbon double bond? Recall that when sp2 hybrids are formed, a pz orbital does not mix to form the hybrids. Each carbon atom has a 2pz orbital, perpendicular to the sp2 hybrids. that contains the fourth valence electron. The two pz orbitals can overlap in a side-to-side fashion. This type of covalent bond is called a pi bond. The electron density is concentrated above and below the plane of the nuclei of the bonding atoms. In a pi bond, electrons are shared. In other words, the two electrons are free to move through both regions of the bond. A double bond is composed of one sigma bond and one pi bond. Lastly, rotation does not occur about a double bond. For rotation to occur along the carbon-carbon bond, the pi bond would have to be broken. First, consider the Lewis structure of acetylene. Counting the number of VSEPR pairs of electrons around carbon 1, we find 2 VSEPR pairs. Recall that double and triple bonds are counted as single bonds in the VSEPR model. You should also count 2 VSEPR pairs around carbon 2. The VSEPR model predicts that the geometry about each carbon atom is linear. In valence bond theory, two sp hybrid orbitals have a linear arrangement. We can begin to explain the bonding in acetylene if we assume each carbon atom is sp hybridized. Each hybrid orbital will contain one electron, meaning that for each carbon, we have accounted for 2 of its 4 valence electrons. The bond formed between the two carbon atoms is called a sigma bond. A sigma bond is a covalent bond formed by orbitals overlapping end to end. The electron density is concentrated between the nuclei of the bonding atoms. In this sigma bond, 2 electrons are shared between the carbon nuclei. When we add the hydrogens, the remaining sp hybrid orbital on each carbon forms a sigma bond by overlapping with a hydrogen 1s orbital. 2 electrons are shared in each sigma bond. There are still 2 more bonds to explain. Which orbitals overlap to form the second and third bonds of the carbon-carbon triple bond? Recall that when sp hybrids are formed, a pz and a py orbital do not mix to form the hybrids. Each carbon atom has both a 2pz and a 2py orbital that can overlap. Each p orbital contains 1 valence electron, accounting for the third and fourth valence electrons for each carbon atom. Both the 2pz orbitals and the 2py orbitals can overlap in a side-to-side fashion. This type of covalent bond is called a pi bond. The electron density is concentrated above and below the plane of the nuclei of the bonding atoms. In each of the pi bonds, 2 electrons are shared. In other words, the electrons are free to move through both regions of the bond. A triple bond is composed of 1 sigma and 2 pi bonds. For rotation to occur along the carbon-carbon bond, the pi bonds would have to be broken.